In this video, we solve our first problem using variation of parameters. This is problem number 7 in section 4.6 of Fundamentals of Differential Equations and Boundary Value Problems by Nagel, Saff, and Snyder. We've got this differential equation right here. And notice that the corresponding homogeneous equation has constant coefficients. So we already know how to solve that. That will allow us to find a fundamental set of solutions. Since the differential equation is a second order differential equation, that fundamental set of solutions has two functions, y sub 1 and y sub 2, and they'll be linearly independent from each other. Now, notice that the right-hand side is not a polynomial, an exponential function, a sine or cosine function, or a sum or product of those, a finite sum or product of those. Instead, we've got an exponential times a log function. Since I've got an exponential times a log function, the method of undetermined coefficients is not appropriate here. So we have to use variation of parameters. Now, whenever you're solving a differential equation, a non-homogeneous differential equation, the first thing you want to do every time is you want to solve the corresponding homogeneous equation. So the corresponding homogeneous equation just is the differential equation, almost, but instead of having this right-hand side, it has the right-hand side set equal to 0. Since this has constant coefficients, we will solve by letting y equal e to the mx. We assume that that is the form of our solution, and then we compute y prime and y double prime. The first derivative of e to the mx is e to the mx times the derivative of the inside by the chain rule, which just leads to an extra m. And then we bring that m down and we say, what's the derivative of e to the mx? It's e to the mx times the derivative of the inside, which is an extra m by the chain rule. And then we substitute these guys into this differential equation. So our equation becomes this equation, that y double prime plus 4 times y prime plus 4 times our initial assumption for y, which was y equals e to the mx. And then we factor out the e to the mx. And then we say this times this equals 0 if one of these equals 0, but the exponential is never 0. So we have m squared plus 4m plus 4 equals 0. That's our characteristic equation. So we substitute into the differential equation and we simplify. We factor out the e to the mx, we divide it out. Or you can just say the only way this product is 0 is if this is 0 because this is never 0. And that leads to that characteristic equation. Now this is a polynomial equation that the values of m have to satisfy in order for e to the mx to be a solution to this equation. So if you can find the values of m that cause this polynomial function to equal 0, then you can find functions that satisfy this differential equation. So we'll solve this by factoring. Two numbers that multiply to give me 4 that add to 4 are 2 and 2. So that's m plus 2 squared equals 0. So we've got one root, or we can think of that as a repeated root. m1 and m2 are both equal to -2. Since we have a repeated root, the first linearly independent solution is y equals e to the m1x. That's y equals e to the negative 2x. And the second solution is x times e to the m1x. So that's x times e to the negative 2x. So you solve for m1 and m2. And then you get y1 and y2. And then you say that y sub c is c1y1 plus c2y2. Okay. Now, in order to use variation of parameters, the coefficient of y double prime has to be 1, and it already is, so we're good there. That means this function on the right-hand side would be called f of x, and it looks like I've been using the wrong variable the whole time. It looks like our independent variable is supposed to be t, not x, but I'll change the problem so that I don't have to change the rest of my work here. I'll just make that an e to the negative 2x times natural log of x instead of e to the negative 2t times natural log of t. So it's a modification of this problem. I've just changed out the independent variable. Okay, so with this in mind, since the coefficient of y double prime is 1, this is our f of x. And that's going to be important when we apply variation of parameters here. So we'll say, let's look at this differential equation. So we will let y sub p equal u1 y1 plus u2 y2, where u1 and u2 are non-constant functions. So they have to be functions of x. And then we'll say then, by variation of parameters, the following is true. Now we're skipping some steps because there would be a lot of cancellations, a lot of differentiation and algebra, but every single time we are led to this conclusion. By variation of parameters, u1 prime will equal w1 over w, where w1 is the determinant of a matrix. You replace that first column with 0 and f of x. Well, the Wronskian is what goes in the denominator, the Wronskian of your two functions, y sub 1 and y sub 2, the two linearly independent solutions of the corresponding homogeneous problem. And then w1 comes from just taking that first column and replacing it with 0 and f of x. So u1 prime is equal to this, and u2 prime is equal to this. You have the Wronskian in the denominator, and this time for the second variable, you leave the first column alone, and you swap out that second column with 0 and f of x. Now, if you're wondering where this came from, watch the video about the derivation of the formulas. I will show you exactly where this comes from. It comes from the assumption that y sub p equals u1 y1 plus u2 y2, and then we differentiate twice, we substitute into the differential equation, we take advantage of the fact that y1 and y2 are solutions to the corresponding homogeneous problem, and then we end up with this equation. It's one equation with two unknowns, and then by making an assumption, we can get it down to two equations and two unknowns, and then we solve using Cramer's rule. And this is the result of Cramer's rule. So we say by variation of parameters, if you make this assumption, eventually you're going to get to this point. u1 prime and u2 prime are equal to this. I'll want to see the formulas for W, W1, and W2. And then I want to see you calculate those. Now, with these two functions up here, It doesn't matter which one you call y1. This one could be y1 and that one could be y2, or the other way around is fine. You just have to be consistent. Once you decide that one of them is y1 and the other one is y2, make sure you stick with that so that these are multiplying the right functions over here in your y sub p at the end. So then we're going to, we've got our formulas, so we need to compute those three determinants. So I'll compute the Wronskian first. And y sub 1 was the e to the negative 2x. The derivative of e to the negative 2x is e to the negative 2x times the derivative of the inside, which is a negative 2. And then y sub 2 is x times e to the negative 2x. So we'll have derivative of the first times the second, plus the derivative of the second, which is negative 2 times e to the negative 2x times the first. And if we simplify that, and we can simplify that by factoring out the e to the negative 2x over here. We get a 1 minus 2x times e to the negative 2x. Okay, now when you evaluate this 2 by 2 determinant, you just multiply across this diagonal and multiply across that diagonal and subtract. So we're going to have 1 minus 2x times e to the negative 2x times e to the negative 2x. You add the exponents there. And then we subtract this. We're subtracting a negative, so that's adding 2 times x times e to the negative 4x. And so I end up with a negative 2x e to the negative 4x over here and a positive 1. So these guys actually simplify and we're left with just a single e to the negative 4x. Now, if you're not sure that you agree with that, you just distribute and you'll have the e to the negative 4x minus 2x e to the negative 4x plus 2x e to the negative 4x, and those will reduce, and you just have the 1 times that, as that's your Wronskian. So we computed w, and then we want to compute w1. So you take your first column and you swap out this column for 0 and f of x. The second column stays exactly the same. And we've already computed the second column. So that's this. Now our first column is 0 and f of x, where f of x is the right-hand side. And the right-hand side of the differential equation was negative 2x times natural log of x. Now remember that has to have, or the differential equation has to have a coefficient of 1 here. If it doesn't, that's not f of x. It's not the f of x that we derived or that was used in our derivation of these formulas. So we need to make sure that that's a 1 before we identify f of x, and this time it is. So f of x is e to the negative 2x times natural log of x. And then in the second column, we've got x times e to the negative 2x and 1 minus 2x times e to the negative 2x. When you multiply across this diagonal, you get 0, and then you multiply across this diagonal, and you're going to get x times natural log of x times e to the negative 4x. So it's this 0 minus that, so we're going to end up with negative e to the negative 4x times natural log of x. That's our w sub 1. Now we want to find w sub 2. And w sub 2 comes from taking the Wronskian, leaving the first column alone, and switching out the second column for 0 and f of x. So we had an e to the negative 2x here, and then a negative 2 e to the negative 2x. Second column is 0 and e to the negative 2x times natural log of x. Multiply across this diagonal, you get e to the negative 4x times natural log of x. And then you multiply across that diagonal, you get 0, and then you subtract. That's your w sub 2. So now you've got u1 prime and u2 prime, because u1 prime was w sub 1 over w. So that was negative e to the negative 4x times x natural log of x divided by the Wronskian, which was e to the negative 4x. So those reduce. And now I have u1 prime equals this, but I need u1. So u1 is, of course, the antiderivative of the derivative of u1. So I would use integration by parts here. Let this be u, everything else is dv. Oops, I'm not really leaving myself enough space. Let me leave myself more space. So we'll have u here, du here, v here, and dv here. dv is x dx. U is natural log of x. So we differentiate to find du. So you get 1 over x times dx. And then you anti-differentiate to get v. So you add 1 to the exponent and divide by the new exponent. Then you multiply across this diagonal and multiply across that diagonal and subtract. And so we get u times v, so that's 1/2 x squared natural log of x minus the integral of v du. 1/2 x squared times 1 over x is 1/2 x. And then you'll just use the power rule for this. So bring that 1/2 down, then you'll add 1 to the exponent, divide by the new exponent, add a constant of integration. Now remember, we're going to take this u1 and we're going to multiply by y1. That's y sub p. It's going to be u1 y1 plus u2 y2. But if I have a constant here and I distribute a y1 through that expression, I'd have a constant times y1 in here, and I don't really need a constant times y1 in here as a term in y sub p, because I already have a constant times y1 in y sub c. So I will let this c be 0. For that reason. So now we've got u1, it's equal to this, and we also know the formula for u2 prime. u2 prime turned out to be that w2 over w, and w2, we calculated that here. And the Wronskian was e to the negative 4x, so these guys reduce. And so we've got u2 prime is equal to this. So that means u2 is the antiderivative of u2 prime. So that's the antiderivative of natural log of x. And we'll use integration by parts again. This is u, this is dv. Remember, when you're using integration by parts, well, first, let's talk about how we evaluate integrals. You ask yourself if you've got a basic rule for that. If you do, you apply it. If you don't have a basic rule, then you do a u substitution. And if u substitution is not appropriate, then usually integration by parts is appropriate. Now, if there is a natural log or an inverse trig function in your integrand, that's usually your u. Everything else is dv. If there's no natural log and there's no inverse trig function, then use typically the polynomial, and you would probably want to use tabular integration at that point. So we'll let u be natural log of x, and dv is just dx. Take derivative of u, that's 1 over x dx. Then you take the antiderivative of 1 and get x. And now when we take this antiderivative, we get u times v minus the integral of v du. So we have x natural log of x minus the integral of x times 1 over x dx. Now don't make the mistake of anti-differentiating this and anti-differentiating that and multiplying them. The answer is not 1/2 x squared times natural log of the absolute value of x. You got to simplify this first. The x's reduce. We're just taking the antiderivative of 1 with respect to x. So we've got x natural log of x minus antiderivative of 1, which is x, plus a constant, And we're about to multiply u2 by y2. So we don't need a constant times y2 as part of our y sub p, because we already have a constant times y2 as part of our y sub c. So we'll choose this constant to be 0. And then that's enough. We've got u1 and u2. So y sub p can be written down now. It's u1 y1 plus u2 y2. And u2 happened to be 1/2 x squared natural log of x minus 1/4 x squared. And that's being multiplied by y2, or excuse me, by y1, which is e to the negative 2x. And then we're adding u2, so that's x natural log of x minus x times y2. And y2 is x times e to the negative 2x. Now there's probably some simplification that we can do if we distribute. So I'm going to do some distribution. Got 1/2 times e to the negative 2x times x squared natural log of x from here. And then we'll distribute the e to the negative 2x there as well. And then we distribute this guy. So we'll have e to the negative 2x, x times x is x squared times natural log of x. And then we're subtracting x squared times e to the negative 2x. Okay, so these guys are like terms, and these guys are like terms. So I've got one of these over here and 1/2 of those over there. So that means I've got 3/2 e to the negative 2x times x squared natural log of x. And then I've got a negative 1/4 and a negative 1 of these. So that's negative 5/4 of those. And it looks like we could factor out an x squared and an exponential if we wanted to. We could even factor out a factor of 1/4. Would get rid of all the fractions. I think I will leave the fractions in there though, but I will factor out that x squared times the exponential. So we've got x squared times the exponential times 2/3 natural log of x minus 4/5 or 5/4. Yeah, and we've already factored out everything else. So that's our y sub p. And y is equal to y sub c plus y sub p. So that's c1 y1 plus c2 y2 plus y sub p, which is this. That's true on negative infinity to infinity. Okay. So let's go through the method and then I will outline the steps for you again. So the first thing you want to do is, well, check on your independent variable. I didn't, so you can learn from my mistake. But then after you've done that, write down the corresponding homogeneous equation and then solve it using whatever method you know. So this happened to be a constant coefficient homogeneous linear equation. So we could let y equal e to the mx, and that would allow us to solve it. So we have y equals e to the mx here. We take the first and second derivative, and then we evaluate this homogeneous equation at y and y's derivatives, because we're assuming that y equals e to the mx is a solution of that equation. If that's a solution, then this has to be true. So we're saying, okay, if this has to be true, what must m be? Well, if this is equal to 0, that means this is equal to 0. Exponentials are never 0. So we have this polynomial must be 0. That polynomial can be solved. Turns out we have a repeated root. M1 and M2 are both equal to -2. So we have two linearly independent solutions, e to the negative 2x and x times e to the negative 2x. Then the complementary function or complementary solution is a constant times the first solution plus a constant times the second solution. Then you look at this differential equation and you say, okay, I want to find y sub p now. Can't use method of undetermined coefficients because the right-hand side does not have the right form. That extra natural log means the requirements for the method of undetermined coefficients are not satisfied. The right-hand side would have to be an exponential, a polynomial, or a sine or cosine function, or a product or sum of those, a finite product or sum of those. And we've got this extra natural log factor. So we've got to use variation of parameters. So we'll say y sub p is equal to this for some non-constant functions u1 and u2. Then by the method, u1 prime is equal to this and u2 prime is equal to this. Now I skipped a bunch of steps there, but remember what we did when we derived these formulas. We took the first and second derivative of this. We substituted into the differential equation. We said since y1 and y2 are solutions, a bunch of terms would zero out. And then we said if we make an assumption that one expression involving u1 prime and u2 prime is equal to 0, then another expression involving u1 prime and u2 prime would have to equal f of x. So we ended up with 2 equations and 2 unknowns, which we could solve with Cramer's rule, which led to this. Okay, so all of that is built into this, but we get to skip all those steps. So we say if y sub p equals this, then u1 prime must be this and u2 prime must be this. So then we just say, okay, let's evaluate those so that we can get u1 prime and u2 prime. W is the Wronskian of that fundamental set of solutions, the one with y1 and y2 in it, and you found those earlier. So we just evaluate that here. Then you find w1. Next, that's here. You just swap out that first column with 0 and f of x, leave the second column the same. Then you find w2, swap out the second column with 0 and f of x, and then you substitute w1 and w2 into u1 prime. So you're going to find u1 prime, which is w1 over w, and then you compute u sub 1 by just taking an antiderivative. U sub 1 is, of course, the antiderivative of the derivative of u sub 1. Then later, we find u2 prime. We already know the w's, so we take their quotient, and then we compute u2 by taking an antiderivative of the derivative of u2. And in both cases, you're going to choose the constant of integration to be 0. Because we're going to multiply u1 and u2 by y1 and y2, and we don't need a constant times y1 or a constant times y2 as a term or as terms in our y sub p. So we've got this, and we're doing this. Okay, and then we go down here and we say, well, we already know u1 and u2 now, so let's just substitute those into the form of y sub p. And then simplify. If it simplifies, go for that. Go ahead and do that. And then the general solution is y equals y sub c plus y sub p. And oops, I stated an interval of existence that's incorrect. That original differential equation had a natural log in it, so it should actually be 0 to infinity. Because natural log is only well defined for an argument that is strictly positive. Sorry about that. Okay, so that's variation of parameters. We'll do another example in the next video.